In a previous class session, we were unable to finish notes 1.4, continuity and one-sided limits. So I thought I'd create this video to finish those notes. I believe we got to about this point right here with example 12. So we're asked to find the x values, if any, at which the function is not continuous. State whether the discontinuities are removable or non-removable. For removable, as a reminder, that would be a point discontinuity. For non-removable, that would be either jump or infinite. All right, so the first task is to find the x values at which the function may not be continuous. So in example 12, we have a piecewise function. Either y is equal to negative 2x as long as the x values are less than or equal to 2. So negative 2x by itself is just a linear function. So it's continuous everywhere, except for possibly at the break of the x value of 2. Okay, or the second piece is y equals the quadratic function x squared minus 4x plus 1 as long as we choose x values greater than 2, but not or equal to 2. And the quadratic function right here is continuous across its entire domain. So really the place that we want to investigate is what's happening as the linear function ends and the quadratic begins at x equals 2. So really the only point to investigate is x equals 2. All right, so if it's continuous, then step 1, part 1, is a 3-part continuity test. Part 1 says that in order to be continuous, the function has to be defined at x equals 2. So for the function at x equals 2, x equals 2 belongs to the top piece because of the or equal, but not the bottom piece. So let's plug in 2 for the top piece. That's negative 2 times 2, so that's just negative 4. In order to be continuous, not only does part 1, the function, have to be defined at that x value, but the left limit and the right limit have to exist and they have to equal each other. So let's investigate what's the limit as x approaches 2 from the left. Well, numbers that are to the left of 2 are smaller than 2 or less than 2, so that puts me on this piece right here. So let me go ahead and plug in 2 to negative 2x. We've already kind of done that up here, so we get negative 4. Let's investigate the right limit. So as x approaches 2 from the right, numbers to the right of 2 are bigger than 2, greater than 2. So this is greater than 2. So now we're going to plug 2 into the bottom piece. Oops. Let me write down the function first. All right, let's see if I can do that. Let's see, 2 squared. 4 minus 8, negative 4, plus 1 more is negative 3. So we can see the left limit and the right limit do not equal each other, so we can stop with the 3-part continuity test right here. And we can say, therefore, f is not continuous at x equals 2. So just quickly plugging 2 into both top and bottom, we can see that we don't get the same y values. So right away, that tells us the function is not continuous at x equals 2. To state whether the discontinuities are removable or non-removable, well, because the left limit ends at a different y value than the right limit, okay, we can say that this is a jump discontinuity. So therefore, it's a non-removable discontinuity. Okay, in 13, we have another piecewise function. The top piece is our tangent pi x over 4. And this function we only care about as long as the absolute value of x's are less than 1. What this statement means is we have to be within 1 unit of 0. So let me just kind of draw a quick number line. So here's 0. If I want this function, I have to stay within 1 unit of 0, less than 1 unit. So that means if I go out to negative 1, anywhere in here, I might have the tangent graph. And then I have to stay within positive 1 over here. I'm going to put a little parenthesis, not a bracket, since I don't have an or equal. So this tangent pi x over 4 when I graph it, I'm only interested in that part of that graph that falls between x equals -1 and x equals 1. Well, that tangent graph is going to be continuous anywhere in this select interval of x's. So really, we're probably just going to want to investigate what's happening at x equals -1 and x equals 1. So let's drop down to the second piece. So the second piece says y can be equal to x as long as x is greater than or equal to 1. So again, on a number line, let's put 0 on there. I want to be more than 1 unit or exactly 1 unit away from 0, greater than or equal to 1 unit. So here's 1. So I'm going to do a bracket, and I'm actually going this way. So I want y equals x when x is greater than or equal to 1, whatever that function looks like. And then likewise at -1, I can be more than 1 unit away from 1 if I'm over at -1 and I stay over in this region. So the tangent graph is going to fall somewhere in between these two x values, whereas y equals x is going to fall on the outside of -1 and 1. So I know tangent pi x over 4 is continuous on -1 to 1. I also know y equals x is continuous everywhere. So the only places I'm concerned about are how these graphs come together at -1 and 1. So let's test x equals -1 first. Test x equals -1. So for the three-part continuity test, 1, is this function defined at -1? Well, I'm coming up here and I'm going, it has to be on this piece right here. X is greater than or equal to 1 unit away. So if I put -1 in for x, I'm going to get -1. So I know there's a point there. 2, let's test the limits. What happens as the limit as x approaches -1 from the left? Well, if I'm at -1 and I'm to the left of -1, that wouldn't be the tangent function. It would have to be the linear function. So as I approach -1 from the left, here's -1, I'm to the left of it. I'm on this piece right here, y equals x. So that limit, when you plug in -1, is -1. So far so good. Let's test the right limit. So what's the limit as x approaches -1 from the right of -1? Well, here's -1. If I'm to the right of it, I'm in this area. So that puts me on the tangent function. All right, so plug in -1 for x. What's the tangent at -pi/4? Using a unit circle to help us, the tangent at -pi/4, -pi/4 is here. The x and y coordinates are positive square root of 2 over 2 and negative square root of 2 over 2. Tangent is y divided by x. When you divide these two, you do get -1. So for part 3, we know the functional value, which is -1, is equal to the limit as x approaches -1. And I would just put f of x here, since when I approach -1, I have two pieces. So let's just put the generic f of x here. So now we know that this graph is continuous at x equals -1 because I ran through the three-part continuity test. Well, there's also another break at 1, so we're going to have to do the same three-part continuity test to test x equals +1. Step 1, is the function defined at 1? Well, x equals 1 belongs here. Plug in 1 for x, and we get 1. Part 2, let's test the left and right limit. So what's the limit as x approaches +1 from we'll do the left first. If I'm to the left of 1, so remember here's 1, if I'm to the left of 1, that means I'm on the tangent graph. Plug in 1 for x. Tangent of pi/4 is up here. Okay, y divided by x would be 1. Let's test the right limit. The limit as x approaches 1 from the right. Here's 1. To the right of 1, I would be on the linear function. So I'd put x, plug 1 in, I get 1. So therefore, parts 1 and 2 are equivalent. So f of 1, which is 1, is equal to the limit as x approaches 1. Okay, so what that tells us is there's no breaks, there's no jumps. So that means that I'm going to come up here and put f is continuous. So going back to the question, find the x values, if any, at which f is not continuous. The only suspicious places were x equals -1 and 1. We investigated both those x values, and we found out that the function is continuous across its entire domain. All right, we're going to continue to use the continuity test in questions 14 and 15. All right, it says find the constant a or the constants a and b such that the function is continuous on the entire real number line. Okay, so we're going to use the three-part continuity test to help us find the missing coefficient here, the constant value on this linear function that would make certain that this piecewise function is continuous. So really for us, the only point of concern is where the break in the x values are, and that's at 1. So let's apply the three-part continuity test here. So the function evaluated at 1 equals, well, I'm not going to plug 1 into the bottom piece because there's no or equal. I'll plug 1 into the x of the top piece, so 3 times 1 squared is just 3. So I know the functional value, or the y value, is 3 when x is 1. Part 2, let's investigate the one-sided limit. So the limit as x approaches 1 from the left. Numbers to the left of 1 are smaller than 1 or less than 1, so I'm going to choose the less than symbol. So I'm going to choose the linear function ax minus 4. I'll plug 1 in for x and get a minus 4. All right, the limit as x approaches 1 from the right. Numbers to the right of 1 are greater than 1, so the greater than symbol belongs here, or is here. Plug 1 in. Okay, well, let me bring down 3x squared. Then plug 1 in for x, and I get 3. And I knew that from up here already. In order for this to be continuous, the left and right-hand limits have to equal each other. So that's why I'm going to set the left limit and the right limit equal to each other. So a minus 4, whatever that value is, must equal 3. And from here, I just have an equation that I can solve by adding 4 to the other side. So if the a value is 7 up here, then I know that when I plug 1 in for each of these pieces, that I would get 3, and that would make this function continuous. Okay, notice in problem 15 we have actually 3 functions. They're kind of scattered, but let's see. This says y equals 2 as long as the x values are less than or equal to -1. So kind of a quick little illustration here. Y equals 2 when x is less than or equal to -1. Well, here's -1. All my y values have to be 2 as long as I'm less than or equal to -1. I'm going to jump down to the third piece. Y equals -2 as long as x is greater than or equal to 3. So let's come over here to x equals 3. When x is greater than or equal to 3, my y values are down here at -2. So I've kind of got the ends, the top and the bottom piece, and what it says is y equals this line, linear function, between -1 and 3. So the only way this can be continuous is if I have some type of line that connects these two horizontal pieces. So we're trying to find A and B such that that would occur. So we actually have 2 breaks. We have a break at x equals -1 and x equals 3. So we're going to use three-part continuity test on both x equals -1 and x equals 3 to see if we can somehow find the values of A and B. So let's test x equals -1. 1. Does the function exist at -1? Yes, -1 is included in the top piece. So that must mean the y value is 2. Let's find the left limit as x approaches -1 from the left. Well, numbers to the left of -1 are smaller or less than -1, so that must mean I'm on the piece that's y equals 2, so I'll put 2 here. There's no x to plug -1 into, so that left limit is just 2. And that makes sense from this visual. All right, what's the right-hand limit? As x approaches -1 from the right, numbers to the right of -1 but close to -1 are greater than -1. So this inequality statement says x is greater than -1. So we bring down ax plus b. Evaluate the limit at -1, and I get -a plus b. In order for this graph to be continuous at x equals -1, the left limit and the right limit have to equal each other. So I'm going to set 2 equal to -a plus b. Well, right now I can't solve for either a or b because I have 2 unknowns and only one equation. So I'm going to kind of leave this on hold while I come over here and I test what's happening at x equals 3. So 3-part continuity test on x equals 3. So 1, the function evaluated at 3. Well, 3 belongs to the bottom piece because of the or equal. So when you plug in 3 for the x, which there isn't one, the functional value is -2. And then let's look at the left and right-hand limits. As x approaches 3 from the left, to be to the left of 3, those are numbers less than 3, so I'm going to be using the linear piece. Where I see x, I'll plug in 3, and I'm going to get 3a plus b. Right, as I approach 3 from the right, numbers that are bigger than 3, that would be the bottom piece. There's no place to plug in 3, so my answer is just -2. So in order for this limit to exist, the left and right-hand limit have to equal, so that means 3a plus b has to equal -2. So at this point now I have 2 equations with 2 unknowns, so we're just going to solve this system. You can use the substitution method by solving for isolating for either a or b up here and subbing it in for the other a or b in the other equation. Or I'm actually going to take both of these equations and I'm going to use the elimination method. So -a plus b equals 2. And then lining up underneath that, I'm going to put the a, 3a plus b equals -2 equation. The elimination method says when you look down vertically, I'm going to try and cancel either the a's or the b's. In this case, I'm going to try and cancel the b's, but I need to first multiply the top equation by a negative so that the b becomes negative, so when I add down, they cancel. So I'm going to just multiply everything in the top equation by -1. I think I'm going to have to come over here. So changing all the signs, I'm going to get +a minus b equals -2. Lining it up underneath, 3a plus b equals -2. And then I'm going to vertically look down, collect like terms. I get 4a, these will cancel, equals -4. Divide both sides by 4, and I'm going to get a's value to be -1. Now to find b, I just need to plug in -1 to either one of these 2 equations. So if I plug in -1 for a, take the opposite, that's 1. 1 plus b. So if I have 2 equals 1 plus b, I could subtract the 1 from the 2, and b is going to be a +1. And finally on the back, this page focuses on the intermediate value theorem. To help us understand this theorem, this application problem, this focus on weight, may help us understand what's going on in this kind of cumbersome formula or theorem. I might recommend maybe just pause the video, read through this scenario right here, and see if you can answer the questions related to that scenario. All right, Today, Joel, who is 17 years old, announced to his math class that he weighs 150 pounds. He also said that on his 10th birthday, he weighed 90 pounds. Consider the following questions about his weight in the time period between his 10th birthday and his 17th birthday today. Did Joel ever weigh exactly 132 pounds? Yes. Did he weigh 120 pounds? Well, yeah, you can't go from 90 to 150 pounds without passing through 120. And did he ever weigh this amount right here? Both of which are yes. Did he have to have been every single weight from 90 pounds to 150 pounds? Yes. Why? Because weight is continuous. Make a generalization about Joel's weight as a function of time. Joel's weight must take on every pound from 90 to 150. Take on every pound from 90 to 150. This is true because weight is a continuous function over time. And this weight scenario is a real world example of the IVT, the intermediate value theorem. So think of the word intermediate as in between, and value just means a y value. All right, so here's the theorem. If f is continuous, like Joel's weight, we can consider his weight a continuous function on a closed interval. Closed means brackets, open means parentheses. Closed means you can include the endpoints. So if his weight is continuous on the closed interval of his age, so in this case, A would have represented his 10th birthday, B would have represented his 17th birthday. So these are our independent values. His weight depends upon his age. Age is independent, weight is dependent. So if his weight is continuous on his age from 10 to 17 years old, and his two weights are not the same, meaning 90 and 150, which they're not, and K is any weight between 90 and 150, then there had to have been at least one number C or age between 10 and 17 such that his weight was that K value. So if K was 120 pounds, then somewhere between his 10th and 17th birthday, he had to have weighed 120 pounds. So simply, the intermediate value theorem says that continuous functions must take on every value between the two y values at the endpoints. We can't skip values. All right, so what does that look like in maybe not a problem situation, a scenario like Joel's weight? What does that look like more analytically in what we deal with? So it says, for the following, verify that the IVT applies to the indicated interval and find the value of C guaranteed by the theorem. All right, so how do we verify that the IVT applies? Well, first of all, we have to make sure we have a continuous function. This is a polynomial function, quadratic, polynomial. All polynomial functions are continuous. So we have to have a continuous function and a closed interval. So the two parts that are important to verify that we can use the IVT is that the function is continuous and we have a closed interval. Well, we know this quadratic, this parabola-shaped graph is continuous, and we have a closed interval because of the brackets, not parentheses. So think of this as your A and your B, or x equals 0 to x equals 5. And it says, verify or find the value of C guaranteed by the theorem. So here's C. So this is a y value of 11. Is 11 between the two y values that are generated from these endpoints? Okay, well, let's just look at a graph real quick. So in y1, I've got x squared plus x minus 1. I'm going to go to my window. All I care about is the smallest x being 0 and the biggest x being 5. Look, I can graph it right now, and there's the parabola. I don't want this entire parabola. I only want this parabola when x is 0, so down here, and x is 5, somewhere up here. So adjusting my window to 0 and 5. I'm not quite sure what my y's are going to be yet, so let me graph. I can see that y value, but I can't see that y value. I want it to go off to the right side of the screen. So I need more y max. So maybe 30. I'm just going to count by 5s. That's what the scale is. All right, so that's just a portion of that parabola. All right, so we want to verify that 11, which it seems to be, 11, a y value of 11 is between the y value here at the left endpoint of x equals 0 and the right endpoint at x equals 5. The way we do that is we go ahead and take the function, evaluate it at 0. So 0 here, 0, 0, negative 1. So think about the point 0, 1 being right here. Now let's plug in the other x value, the b value, 5. So that's 25 plus 5 minus 1. So the point 529 is at the right endpoint. So this is 1, 2, 3, 4, 5. That must be 29. So if that's negative 1 and this is 29, then 11 is certainly going to fall between negative 1 and 29. 11 would be about right here. Somewhere going across there. So how do we show that? We just show that 11 is greater than negative 1, but less than 29. If you want to get real fancy, we know that negative 1 is equal to the function notation f of 0, and we know that 29 equals f of 5. Either one, whichever way WebAssign would like it. We're not done. Then it says, find the value of c where the y-coordinate is 11. So if the y-coordinate is 11, I'm going to plug 11 in for f of x. So let's find c. So 11 equals x squared plus x minus 1. Now they're talking about a c value. You could use just x, that's fine. Or if you want to customize and change all the x's to c's, that's fine too. Me, preferably, I just keep with x's and know that that x is equal to that c. All right, so I'm going to subtract the 11 to the other side, so that'll zero out the 11. So c squared plus c minus 1, but minus 11 more is minus 12. This is quadratic. I'm going to factor it. So 0 equals the two binomials that multiply and give us that quadratic would both have a c up front, because c times c is c squared. Factors of negative 12 that add to 1 would be plus 4 and minus 3. Set each factor equal to 0. So from this factor, c plus 4 equals 0, which means c is equal to negative 4. C minus 3 has to also equal 0, so that means c equals 3. Well, going back up to my interval between 0 and 5, negative 4 does not fall in that interval, so that we discard that, just lightly cross it off. And the final answer, the only answer, is that when the x value is 3, we will have a y value of 11. So going back to your graph, if I hit trace and I hit 3 and press enter, it should tell me that my c that gives me a y value of 11 is 3. Okay, 17, it says, for the following, verify that the IVT applies. Okay, to apply, the graph of the function we're working with has to be continuous and closed. Again, another quadratic. It's polynomial, continuous everywhere. That satisfies one of the conditions of the theorem. I have a closed interval, no parentheses. We can think of this as x equals 0 or a, and x equals 3 or b. Is there a y value of 0 in between the two y values at x equals 0 and x equals 3? Well, let's plug in 0. So 0, 0, that's 8. Now let's plug in 3. That's 9 minus 18 plus 8. So that's -1. So definitely a y value going from 8 down to -1, okay, would pass through a y value of 0. So just to get an illustration of that, let me turn that one, well, I'll just clear that. I'll turn it off. Here's the function. I'm going to turn it on. I'm just going to do zoom 6 first. Quadratic, continuous. Remember, we're only interested in this graph, oops, when x is 0. So go to window, x is 0, x min is 0, x max is 3. I don't quite know what the y, well, now I do know what the y's are. They go from -1 to 8, so my window should be okay. So I can see that 0, 8, this is a y coordinate, and I'm going to journey down to a y value of -1. I have to pass through a y value of 0, the x-axis. So what is the x value that gives me this y value? It looks like about 2. So let's see if we can use our math to support that. First, let me show that 0 is between. This y value is greater than -1, but less than 8. If we want to get fancy, -1's notation is f of 3. 8 can be replaced with f of 0. Now, to find the x value, where my y value is 0, if y is 0, we plug 0 in for y. You can keep the x's or you can change to c's. I'll keep the x's this time. It's quadratic, let's factor. Each binomial will have x and x to give x squared. -4 and -2 would give us the -6. Set each factor equal to 0. Let's check each of these solutions to make sure they each fall between 0 and 3. Oops. 4 does not fall between 0 and 3. We lightly discard it. So we say that our c value is 2. You can keep with x or you can keep with c. Let's look back at our graph. If I hit trace and I hit 2 and I press enter, yes, the y value will be 0. So that's how we'll look at the intermediate value theorem.